Good evening, everyone. I'm Professor Andrei Zvelindovsky, Head of School of Mathematics and Physics at the University of Lincoln. Very warm welcome to everyone who joins us in our Astro-Chats with our distinguished guest, Professor Don Kurtz. Hello, Don.
Hello, Andrei.
I know that many of you are regular visitors, but some always come for the first time. So I'll just briefly mention what this Astro-Chat is about. For first about half an hour will be presentation from Don, followed by another about 25 minutes, half an hour Q&A session. So we are finished in 1 hour, and the main thing what I ask you to put your questions in a live chat under this video, then I'll read it to Dawn and you have opportunity to hear your answer. You also will receive email after the Astro-Chat inviting you to leave your comments, your feedback, which is very important for us to continue with these Astro-Chats. And now I just say a few words about Dawn, in case you came for the first time. Dawn is originally from San Diego in California, and I think some of our members of audience tonight are from California as well. Don spent his undergraduate and research doctorate study in America, first in San Diego State University and then University of Texas in Austin, and which followed with about 25 years work in University of Cape Town in South Africa, where Don actually physically right now as well. After working in South Africa, Don spent another almost 25 years working here in the United Kingdom, University of Central Lancashire in Preston, where we actually met with Don, and in fact I was working there for 10 years as well. Now Don is Emeritus Professor at the University of Central Lancashire, as well as Extraordinary Professor in Northwest University in South Africa. And we're very pleased that Don is also Visiting Professor of Astrophysics, University of Lincoln here in Lincoln. And his long and distinguished career, Don wrote about 500 of scientific publications. He is author of well-known textbook on astroseismology. He spent many nights observing various wonderful things in the sky, served on various committees all around globe, and as recognition of his substantial contribution to the field of astrophysics, Don was awarded 2022 Service Awards from Royal Society of Astronomy. And with that, I'm very pleased to give floor to Dawn and tell us about topic of tonight.
Thank you, Andrei, for that introduction. Good evening, everyone. I'm going to give a little bit of a warning here. I'm in South Africa, and at the moment, my Wi-Fi cable is down, and I'm talking to you and broadcasting through my phone, which I've loaded up with enough data, I hope. But if something happens to that, there may be a 2 or 3 minute pause while I load it back up again to keep myself going. So bear with me if that happens. It shouldn't happen before question time if it happens at all. Just a warning. Now, as you know, we're coming up on the winter solstice. Winter solstice here in the southern hemisphere where I live. Summer solstice for you in the northern hemisphere. And being that winter's coming, of course, where I live in the east coast of South Africa on the Indian Ocean, temperature tomorrow should be 27 degrees, sunny, blue sky, and we'll have a nice walk on the beach for that. So tonight, I want to talk to you about once in a blue moon. Recently, and by recently I mean over the last century, some people have started calling a second full moon in a month a blue moon. It takes 29.5 days for the moon to go from full moon to the next full moon. And so if you have a full moon on the 1st or the 2nd of the month, you can have a second full moon in the same month. Some people call that a blue moon, but that's a back formation. It's a back formation from the expression once in a blue moon, meaning something's very rare. There's some other modern definitions of blue moon too, having to do with full moons, but there really are blue moons. Sometimes the moon's blue, and that's one of the things we'll talk about tonight. And the moon's not blue very often. It only happens once in a blue moon. For us to understand that, we need to talk about waves to start, because we need to understand how light interacts with the air. Now, there's a fantastic picture of a surfer on what looks to be about a 10-meter wave. Today, when I went down to the beach here where I live, the waves were about 4 meters, pretty impressive, but nowhere near as big as what this guy's riding right here. And that's a wave in water. Light is an electromagnetic wave, which can travel through completely empty space, but also through other media. And we'll talk about that. But first, some characteristics of waves. Here's a graphic of an ocean wave. It's traveling from left to right. And it has several characteristics I'd like to be able to use tonight. It has a wavelength, and that's the distance from one crest to the next, or one trough to the next. It has a velocity, the speed with which the wave's traveling. And it has a frequency, how often a wave passes a particular point, how many times per second. It's also got an amplitude, how big it is. We won't be using that, but we will talk about frequency and wavelength for the waves and velocity, particularly for electromagnetic waves. Now, light is just a small part of the electromagnetic spectrum. I'll show you that in the next slide. But the way light works is an electrical particle is perturbed, it moves, and when it moves, it sets up a wave of changing electric field that starts out through space. And a changing electric field creates a changing magnetic field, which you'll see in this graphic is tilted 90 degrees to the electric field. The changing magnetic field creates a changing electric field that creates a changing magnetic field, creates a changing electric field, and the whole thing is self-propagating through empty space, traveling at the velocity of light, 300,000 kilometers per second in empty space. Here's a graph showing the range of the electromagnetic spectrum, of which light is just a tiny part here in the middle. The highest energy is on the left here, lowest energy is on the right. The highest energy electromagnetic waves, gamma rays, and then X-rays. They've got such high energy they can penetrate your body, give you X-rays for medical purposes. And then ultraviolet, which we can't see, but of course some gets through from the sun and you can be sunburned by that. Then the visible, a very short range, infrared rays, which you can feel as heat, and then many kinds of radio waves at long wavelengths. And in the visible range, we spread the spectrum out from blue to red. We call that a spectrum in science. We call it a rainbow, often just popularly, and we'll talk about rainbows in just a little bit. The important characters are that the blue light, the purple light, are short wavelengths. They have a wavelength of 400 billionths of a meter. And then the long wavelength light, the red light, has a wavelength of about 750 billionths of a meter. And so red light has a long wavelength and blue light has a short wavelength. Blue light has also got high energy and red light lower energy. And both of those things are important to us tonight. So high energy to the blue, low energy to the red, short wavelength in the blue, and longer wavelength in the red. This graphic shows an apparent wavefront of light. Sorry, I'm just stopping for a moment, and my Wi-Fi is not back up. I've just been informed it's still down. That's all right, we're on the phone. Here's a wave of light coming in through the air to hit the surface of a glass block. The wave is traveling at nearly the speed of light. Now, light slows down when it passes into air, and then it slows down even more when it passes into glass. And so these waves of light coming down to the surface of the glass, one edge of the wave hits the glass first and slows down. The other edge keeps going at the same speed until it hits the glass, and the net effect is the direction of the wave changes as it passes into the glass. That's called refraction, and we'll be looking at that. Some of the light's reflected off the surface, and the wave comes in at a certain angle to the vertical, it bounces out at that same angle, and that's what we call reflection. And you're fully familiar with that looking into mirrors. In the case of refraction, you would have some experience of this. If you take a spoon and put it in a glass of water, it looks bent. Or should you have a swimming pool, most of you in the UK won't. Those of you in San Diego might have, and you put your cleaner into the pool, it'll look like it's bent where it passes through the surface from this refractive effect. And finally, we need another effect called dispersion. If white light passes into a glass block shaped like a prism, as it passes into the block, it slows down, but blue light slows down more than red light. And so the blue light is bent through a larger angle than the red light, and the light is spread out into a spectrum. By tipping the glass at the other angle, we can get that effect again, where the red and the blue are then spread out into a full spectrum by the dispersion, that is the difference in the different speeds of different wavelengths and different energy of light as they pass through this glass prism. Now there's a picture of a beautiful southern African glossy starling. I took that up in Kruger Park. It's a Cape glossy starling. And you'll see this beautiful iridescent sheen to its feathers, while in the background you see the beautiful blue of the Earth's sky, which we get where we have nice clear air. The reason the sky is blue is that there are aerosols, there are molecules, there are particles in the Earth's atmosphere that have a general rough size of about 300 billionths of a meter. Now, you'll remember from a couple slides ago that blue light has a wavelength of 400 billionths of a meter. Red light, 750 billionths. And so the blue light has just about the same wavelength of these particles in the Earth's atmosphere, and the Earth's atmosphere scatters blue light much better than red light. And so the light that's passing overhead from the sun that wouldn't have been coming to your eyes, some of it is scattered off these particles in the Earth's atmosphere and scattered to your eye, and it's primarily the blue light that's scattered, which is why we have a blue sky. The reason for putting the bird in, this bird has evolved air pockets in its feathers, and the air pockets are approximately 900 billionths of a meter, 900 nanometers in size. And so they too scatter blue light much better than longer wavelengths, and you end up with this beautiful iridescent blue bird. Same physics as the blue from the sky. Now, on a much larger scale, here's a picture of the Pleiades star cluster. The Seven Sisters, about 400 stars, young by astronomical standards, only about 100 million years since this cluster of stars was born. And they are passing through a cloud of dust out between the stars, and that dust is roughly a few hundred billionths of a meter in diameter, and so it primarily scatters blue light. And so the reason that the blue light shows around the Pleiades is the same reason that that bird shines blue and the sky is blue, that particles scatter best light that is about the same wavelength as the size of the particles. Now, the Pleiades has got many other names in other cultures. Here in Southern Africa, amongst the Xhosa people who live here where I live, in the Eastern Cape, or the Zulu people farther north, they call this cluster Isilimela, and it's very important to them to define the time of year when they have the manhood rites for the young men. And all of you listening, I am sure, speak some Japanese, and you'll know the name for the cluster, the Pleiades, in Japanese. If you think you don't know the name of that, you will. The Japanese call this cluster Subaru. And if you think about what the plaque for the company Subaru, who makes the car, looks like, it shows a cluster of stars, this cluster. So that's Subaru, Isilimela, the Pleiades, but it's scattering the blue light for the same reason that the sky is blue. Now, here's a picture I took of a sunset over a Central African lake called Lake Malawi. And of course, the sun goes red when it goes down. The reason the sun goes red at sunset is the same reason the sky is blue. The atmosphere scatters blue light much better than red light. And as the sun sets down towards the horizon, because of the curvature of the Earth and the curvature of the atmosphere, we're looking through more and more and more air the lower the sun gets. Hence, more and more and more of the blues being scattered away, and it's the red that penetrates and comes through. Hence, giving us our beautiful red sunsets. The sunsets are red for the same reason the sky is blue. The atmosphere scatters blue better than red. So how do you get a blue moon? Now, this is not a true picture of a blue moon. This is a Photoshop picture of a full moon, which somebody has colored a nice blue. I can tell you I have seen a blue moon once in my life, And it was blue, but much more pastel and not quite so striking as this, but definitely blue. That happens under rare circumstances when aerosols are blasted into the Earth's atmosphere, where the particles have roughly the size of the red wavelength of light, on the order of 700-800 nanometers, even a micron. How does that happen? After a gigantic forest fire sometimes, Australia, Canada, these massive forest fires, all the globules and aerosols that come out of the forest fire have larger size than the typical particles in the Earth's atmosphere. And as a consequence, they scatter red light better than blue. Excuse me. Volcanic eruptions can do the same thing. It was after Mount Pinatubo eruption in 1991 that I saw blue moons from the South African Observatory out in the Karoo here in South Africa. So the blue moon comes on the rare circumstances when there are particles in the atmosphere that have got roughly the size of red light, and the red light's scattered than the blue light. It is rare. It only happens once in a blue moon, but then you truly do get a blue moon, and you can even get a blue sun. You can get a blue sunset. Here's a red moon. This is from a couple of decades ago, but this is a picture of the moon in 3 different stages passing through the Earth's shadow during a total eclipse of the moon. We had one of these just 2 weeks ago in the last full moon. Here where I live, it happened just at sunrise, and I got up in the morning and sat and watched the moon as it was setting off to the west, passing into the Earth's shadow, and then turning this deep red. Why is the eclipsed moon red? It's in the Earth's shadow. No sunlight can shine on it. You would think that you wouldn't be able to see it. There's no light shining on it. But what's happening is that around the edge of the Earth, as seen from the moon, light is passing into the Earth's atmosphere, and then it is refracted, bent slightly, as we looked earlier at the refraction in that earlier diagram, and it's bent so that it's cast into the Earth's shadow. And the light that's cast into the Earth's shadow is the light that can penetrate through the atmosphere. And that, of course, is the red light. The blue's scattered away. So some red light is refracted into the shadow. And during a total eclipse, it's different on each eclipse, you get a lovely reddish hue to the moon. And that was true 2 weeks ago. Some of you may have seen pictures of that. It was in the news. Here's a young man sitting in a traditional fishing boat carved out of a hollow log, fishing in a lake, and there is a beautiful clear blue lake. But it's a cliche to talk about a clear blue lake. But why are mountain lakes blue? The water's not blue. Water's largely clear. The color of the water, if you actually look into the water, depends on what's suspended in the water. Some seas look beautifully green, some are gray. Just depends on the particulate material in the water, what light's scattered back. But this blue of this lake is a reflection of the blue sky. And your typical clear blue mountain lake is blue just because it's reflecting the sky. There's a picture of just an artistic device, which is fiber optics. Of course, it's these fiber optics that now carry our Wi-Fi signals for most of us. And the reason the light stays inside the fiber is that the light can only hit the edge of the fiber at a very shallow angle. And less than a certain angle, which is called the critical angle, 100% of the energy is reflected. And as a consequence, in these tiny little tubes, once the light goes in, it can't get out again. When it hits the edge, 100% reflection, and it just bounces through the tube and carried down possibly over thousands of kilometers for some of you before it arrives in your home, carrying the signal for your Wi-Fi. So total internal reflection comes from a critical angle, an angle below which all of the light is reflected. And when we look off across a body of water like this, I'm looking at a sunset, once the sun gets low enough, 100% of the energy gets reflected and comes to you along this glitter path. Now, I took this picture from the bow of a ship called the Queen Elizabeth when I was sailing out of Sydney Harbor 2 years ago, just before COVID started. I was lecturing on the ship on a cruise to Papua New Guinea. And next Tuesday, my wife and I fly first to England and then to Vancouver. And I will be lecturing again on the Queen Elizabeth for 2 cruises to Alaska, to the fjords and to the glacier fields over the first 3 weeks of June coming up. What you're looking at here, if this water were completely flat, if there were no wind and the water were flat, you would simply see a reflection of the sun in the water. It would be like a mirror. The reason you see this glitter path is because lots and lots of waves are tipped up at different angles. And if they're tipped at just the right angle, then an image of the sun reflects off of that little spot and comes to your eye. And so the width of the glitter path, when you see this, depends on how rough the water is. The rougher the water, the stronger the wind, the wider the glitter path gets. You can see that on the sun and the moon easily. It's a common effect if you look for it when you're looking out to water at sunset. Here's a beautiful picture by a photographer who took a fantastic lake on an absolutely windless night, exposing the stars, and there you can see the stars are reflected in the lake. The lake just acts like a mirror, and it would do the same for the sun if it were completely flat. The only reason it doesn't over the sea is always rough because the wind's blowing. Now here's a moon that orbits Jupiter. It's called Io. And oh, speaking of Jupiter, for those of you who get up early in the morning, you're in summertime. It gets very light for you early in the morning. But Venus is beautiful in the early morning sky, and Jupiter and Mars above Venus are right next to each other. And over the next 2 days, they're actually going to pass in the sky. And they will come so close together that 2 days from now, Jupiter and Mars will be closer together than the diameter of the full moon in the morning sky. But you do have to get up early to see that. This moon Io is about the size of the Earth's moon, and it's covered in live volcanoes. The volcanoes erupt molten sulfur, and the sulfur forms lakes. And here's a big lake of molten sulfur right here, this black thing that you can see. And you think, well, why should a lake of molten sulfur be black? I mean, after all, sulfur is kind of reddish yellow. And when it solidifies, you can see that for the rest of Io. The sulfur there, where it's turned solid's got this reddish yellow look. Why is the lake black on Io? And the answer is because there's no wind, there's no atmosphere, and it reflects the sky, and the sky is just empty space. If you could stand on the edge of that lake, if you were an astronaut, could stand on the edge of that lake, you would see the stars reflected in that lake, just as you do with this lake here on the Earth. Taking you off to other topics, here are two juxtaposed pictures set to the same scale of two sunsets. On the left is a sunset on the Earth. You'll see the beautiful reddish sunset for the reasons we've talked about. And on the right is a sunset on Mars taken by a Mars rover. And you'll see that the sunset on Mars has got kind of a bluish haze. Now, why is that? And the answer is the atmosphere on Mars is made of carbon dioxide. It does scatter blue light better than red light, but the atmosphere on Mars is so thin that it really can't scatter very much light. And so it doesn't redden the sun very much. The sun, if you look at it carefully, is actually rather yellow-white. It's normal color. And the blue you see around here is that the blue that's being scattered by the sky, the atmosphere is so thin that it's very hard to see. And you only see it close to the sun where the scattering is best. And so that's accentuating the sky scattering the blue light. Notice also that the size of the sun's smaller on Mars than here. Mars is farther from the sun. And so the angular size is seen from Mars. The sun looks smaller. This is an artist's impression of a planet that orbits the nearest star to the sun and the Earth. Proxima Centauri is the star. It's a component of a triple star. Alpha and Beta Centauri so Alpha Centauri is a double star that's often called the closest star to our sun. And I'm talking to you right now, but if I walked out into my front garden right now and looked up, I could see Alpha Centauri right now. It's up near the Southern Cross, easy to see from where I live here. And orbiting about the double star Alpha Centauri, very far away, is a faint red dwarf, Proxima Centauri. Now, it doesn't look faint here because in this particular picture, Alpha Centauri is much further away. But Proxima Centauri has been discovered to have a planet. And that planet's at just the right distance. It could have liquid water. And with liquid water, perhaps it could have life and an atmosphere. That's being explored now, perhaps with the James Webb Space Telescope. When it fully comes online this month or next month, some spectra of the atmosphere of that planet may tell us something about the conditions there. But the artist has made the image here look very reddish because the star that the planet's orbiting is a cool red dwarf that puts out much more red light than our yellow, hotter sun. Here's a picture of a sunset. Many of you will have seen this on sunsets. You watch the sun going down and it flattens. And that flattening is because the air is getting thicker and thicker and thicker as you get near the horizon, as seen from where you're standing. And the refraction is different. And so with the very heavy refraction at the horizon, the image of the sun is lifted. And when you see the bottom edge of the sun just touch the horizon. Actually, geometrically, the sun is just set. And that refraction, the bending of the sunlight through the atmosphere, lifts the whole sun by its diameter, but it lifts the bottom more than the top because the air is thicker down here, and it squashes the sun to give you this weird oblong effect. And then there are layers in the atmosphere, and in those layers you can see ripples along the edge of the sun. Sometimes a little piece will break off the top. And this whole thing, because the atmosphere actually acts as a prism, is dispersing the light, and the sun spread out into a tiny little spectrum with red on the bottom, and it should be blue on the top, but the blue light's scattered away, so the green is what's left on the top. And occasionally on the sunset, if you watch carefully, just as it sets, that last little piece going down is the green bit, and it turns green in what's called the green flash. Some people don't believe the green flash is real. It's very real. I've seen many, many, many green flashes. You need to look for them, and one of the best places to look for them is standing high on a mountain looking down into the sea, and that's a good description of many of the observatories in the world where I've worked: Hawaii, Chile, Western Coast, North America, here in South Africa. And you can then see the green flash on occasion. Of course, Jules Verne wrote a science fiction story about that, the green ray, back at the beginning of the last century, around 1900. And many people thought that it was fictional from his story, but it's a real effect. The green flash happens. This is a picture I took driving down Highway 1 in California. I was coming from NASA Ames Research Center in Mountain View in California, and I was headed to a meeting in Santa Barbara, and I chose to drive down the coast. It was early morning, and I caught the sunrise through the cypress trees near Pebble Beach Golf Course, for those of you who are golfers, along the California coast. And you'll notice in this picture, the sun's there behind the tree, and you can see a sunbeam coming off to the right, sunbeams coming off to the left. Those sunbeams are not really spreading out. The sun is so far away that those sunbeams are parallel to each other. That beam there and this beam there are so close to parallel you couldn't measure the difference. Now, do you find that hard to believe? Well, look at the road. The reason I put this picture in is I'm comparing it to the road. You know that that road is not getting smaller in the distance. It's got a constant width, and yet it looks much wider closer to you and narrower further away. Seems to be spreading out coming towards you. That's a parallax effect, just because in the distance the angle is smaller. And so this effect of the sunbeam spreading out is an effect of parallax. They're not really spreading out. And here's an example of what are called crepuscular rays. There's the sun near sunset. Here's some clouds. The shadow of the clouds are being beamed up into the sky through the brighter scattering of the sunlight off of haze in the atmosphere. And it looks like these sunbeams are separating, but they're not. They're parallel to each other. And on occasion, you can see anti-crepuscular rays. You can turn around and look the other way, and you can see those beams coming right back together again in the other direction. Those things are easy to see. You just need to know to watch for them. This is a lovely picture taken by an astronomer from the top of Mauna Kea in Hawaii. And he's looking east. That's the full moon rising in the east as the sun is setting in the west behind us. This band that you see of light here is the Earth's shadow rising into the atmosphere as the sun goes down. And in desert conditions, observatory conditions, I often see that. You need to live in places where it's clear, there's not too much water vapor in the air and dusty, but then you can see the Earth's shadow rise into the atmosphere as the sun comes down. But this conical shadow here is the conical shadow of Mauna Kea, the great volcano in Hawaii. All mountains cast a conical shadow. And the reason is it's not because the mountain has a peak. Table Mountain in Cape Town, which is rectangular in cross-section, casts a conical shadow. And the reason for that is that these lines going into the distance are essentially parallel to each other. This is the parallax effect again. As they go off, they do eventually converge, but they converge out way beyond the moon. If there were an eclipse, if the moon were in the right place, it would be passing through that shadow. It's off to the side on this particular moonrise. So the conical shadows of mountains are also a parallax effect. Now, rainbows, I told you in the beginning we would talk about them, and there's a lovely picture of a double rainbow. I trust all of you at some time or another you've all seen rainbows, but many of you double rainbows too. And I hope you've noticed, but if you haven't, let me remind you that when you look at a rainbow, the main rainbow is red on the top and blue on the bottom. When you get to see the second rainbow, it's red on the bottom and blue on the top. Now, a rainbow is only a bow because the ground gets in the way. If you could go up in an airplane and look down on a rainstorm with the sun behind you, it wouldn't be a rainbow, it would be a rain circle. The center of the rain circle is directly opposite the sun, and the light for the rainbow is sent out 42 degrees from that and forms a full rain circle. But when you're on the ground, of course, the horizon cuts it off, and so we only see the top part of the circle. And there you can see the double rainbow. Red on the top and blue on the bottom. Well, here's how it happens. The raindrops are roughly spherical. Forget people, artists drawing raindrops as little teardrops. That's not right. The raindrops are spherical in cross-section. The white light comes into the water and it slows down. The blue light slows down more than the red, so it's dispersed off into a rainbow, reflects off the back of the water droplet, comes out the other side. The water droplet acts as a prism, and there the rainbow comes out with the blue on the top and the red on the bottom. Let me just check my data here, folks, to make sure we're not about to get cut off. I'm looking okay, I think. For some reason, it's not losing now. Okay, sorry for that distraction. I just don't want to lose you right now. So I told you the rainbow, it's red on the top and blue on the bottom, and I show you the raindrop, and blue comes out on the top and red on the bottom. Where does this confusion come from? And here's a schematic answer. This is not to scale at all. It's purely a cartoon of some silly man standing here. If he's really looking at a rainbow, the sun's directly at his back, off in the other direction. But the light comes into a raindrop down here, and it spread out with blue on the top and red on the bottom, and the blue light comes to the man's eyes down here. The longer wavelengths, like the red light, hit him farther down. He doesn't see those. He has to look up higher in the sky, where the angle's such that the red comes out to his eye, and the blue on the top goes over his head. And so he sees red on the top and blue on the bottom, because of the dispersion, the different angles that the different colors get spread out into, because blue slows down more than red. The reason why the secondary rainbow has reversed colors is there are two reflections inside the water droplet. And if you like a simple way to explain that, this diagram traces through for you, but a simple way to understand that is that with another reflection, mirrors just produce a mirror image, and it's mirrored from being red on the top and blue on the bottom to blue on the top and red on the bottom. There is a third, fourth, and fifth rainbow, but they're over towards the sun, and they're too faint. Nobody has ever seen those with their eyes. They can be detected in labs under controlled conditions with equipment to detect them, but not seen with the eyes, and they come from more reflections inside the raindrops. I hope sometimes you look up when there's cirrus cloud in the sky. Cirrus, very thin, very high cloud, and it's ice crystal cloud. It's absolutely common in the UK. It's reasonably common through the rest of the world. I often see it where I live here. For me, it normally comes in 1 or 2 days before a cold front. If a rainstorm's coming, then these cold ice clouds will come in. Up at about 20,000 meters, they're very high up. And the ice crystals can then produce wonderful atmospheric effects, such as this 22-degree halo you see right here around the sun. What causes that? Well, we like to think ice looks like this. Beautiful picture inside of an ice cave on a glacier with its blue color. That blue color is just, that's what's penetrating through the ice. Real ice crystals in the sky are shaped like hexagons. They can be long and thin. They can be flat plates, but they're hexagonal in shape. And if you think now, for those of you who live where it does snow, classically, snowdrops are beautiful, beautiful hexagons, all right? They've got lovely patterns to them too, but they're six-sided in shape. And when they turn into an ice crystal, then they're a solid crystal, six-sided. And the light passes through the crystal as if it were a prism. In comes the white light, spread out because it slows down as it moves into the ice, and then comes back into the air, speeds up again, but the angle's changed, and it's spread out into a spectrum. But the ice crystals can be oriented in any direction, so the light can be scattered off in all directions. It turns out that when you do that, it's like working with a prism in a physics lab. For first-year undergraduate physics students, they usually get to do a prism experiment. Some high school students do too. And when you rotate the prism, it changes the angle the light goes off to, but it preferentially goes off to an angle of 22 degrees. And that's what produces that 22-degree halo. There are many other halos depending on the direction that the light travels through the ice crystal. This is a real picture taken by this man in Sweden. And there's the 22-degree halo here. The ice crystals, since they're falling, are primarily vertical in direction, and so they mostly spread the light out to the sides, and that's what produces the two bright spots to either side. Those are called colloquially sundogs. They're 22 degrees from the sun, and they dog the sun. They follow it as it sets. There's a perihelic arc, which is the continuation of those sundogs all the way around the sky. That can go around behind you. There are these wonderful, very, very unusual halos up here that are not seen very often. The circumzenithal arc, I've seen a few times. You can see it. It has a rainbow of colors. It's only just an arc. You'll see it up centered on the zenith when the sun's between 11 and 26 degrees to the horizon. You need to know to look for that. And then there's some much rarer halos over here. There's a 46-degree halo, which is more common. It's this 22-degree halo that's the easiest to see. And if you think that those are rare, it's just a matter that you need to look. But the problem is, when you look up in the sky, the sun has to be there, and the sun's blinding. And so when there's cirrus cloud around and you want to look for halos, put your hand up and block the sun out, and then open your eyes and look. And with the sun blocked out, you can often see these halos. I look for them frequently, and I see them frequently. This is from a website by a man named Les Cowley. This is the best website in the world for atmospheric optics. He calls it AtOptics. It's a UK website. He's got programs where you can actually generate how the halos are formed, wonderful explanations of all the phenomena. So any of you who'd like to follow up on halos, rainbows, and understanding the things we're talking about tonight, this is the perfect website to go to. Les Cowley, Atmospheric Optics, and if you just put AtOptics in to your browser, you'll find that very easily. Some other things that you can look for, not in the sky, interference patterns. Here in a spider's web, the web's strands are equally spaced, and because of that, when you're at just the right angle, the light from one strand and the light from the next strand, the difference between the two strands is some integral number of the wavelengths of color of light. And the waves of light pile up on top of each other, just like waves in the ocean piling up and giving you a big wave at sea. And so at the right angle, the green waves pile up for another angle, the red ones pile up, and you get a spectrum off of what's called a diffraction grating, but in nature with a spider's web. And I've seen this many times too. You simply need to know you should look for it. You see a spider's web early in the morning, late in the evening, the sun's shining on it. Just move your head around and get the right angle. You may well pick this up. You can, of course, see that very easily in a DVD or a CD disc. For those of you who remember what those were back when that the difference between the front and the back of the bubble is a small integral number of the wavelengths of light. It depends on how thick the bubble is. Where you see blue here, it will be thinner because the wavelength of blue light is less, and to get an integer of that, you'll have a slightly thinner bubble. Where you see the red light, it'll be slightly thicker. It's not of uniform thickness. And the place you see this best, since most of us don't go around blowing bubbles, you can see this in oil slicks on the road too, when a rain comes after a long time, and you see a slick of oil on the road, and those colors, same sort of effect, interference from the front and the back of the bubble. And in nature, animals know how to do this. The jewel beetles the world over have evolved chitin in their shells, which is very thin, and the thickness of the chitin is partly transparent, is some integral number of wavelengths of light. Here up on the head of this beetle, an integral number of the wavelengths of green light. So the green coming off the back and the front pile up and appear bright, and down here it will be thicker, longer wavelength to produce red light. And so that's how the beetles produce different colors too, that interference effect. So once in a blue moon, the blue moons don't happen very often, but lots of these other things in the sky are happening all the time. And I hope I have stimulated you to look up more often and see these things for yourself. Let's go to questions. Thanks for your attention. And am I back now, Andrei?
Yes, you are back. And
Okay.
it's now time for questions. Again, we have already some questions in a live chat, and I invite everyone to put questions there. I'll just kind of a small comment when you showed beautiful images of rainbows and soap bubble rainbows. It's interesting that here in Lincoln, already in 13th century, bishop of that time, Bishop Robert Grotest, actually was writing about rainbow. And of course, he was still far away from explanations we have now. But that was fascination for people from Roman times, when first records, and till 13th century. And now we finally know why rainbow is rainbow. But we have lots of questions, so let's go to those questions. The first one was when you showed the bird, and from.
Tell me who it's from, please.
Yes, it's from Jamila Bejalan, who asked, so the bird doesn't have any blue pigment on its feathers.
Yes, Jamila, that's true. That bird does not have blue pigment. Some blue birds do have blue pigment, but that bird is producing the blue from scattering from these little pockets of air pockets in the feathers. And other birds do that too, and they've got pigment. If you think of the hummingbirds of North America or the sunbirds of Asia and Africa, who've got beautiful green iridescence, they've also got air pockets that scatter the light, but then they've got a pigment, melanin. We've got that too, and that absorbs the blue light. And so the next color that comes through is the green. And so they're using scattering again. But you can tell the difference between a scattering bluebird and a bluebird that's got blue pigment, because the bird that's got the scattering effect has iridescence. It's iridescently blue, it shines, whereas the bird that's got blue feathers may be absolutely beautiful blue, but it'll be a more solid, nice, just a nice solid blue that's not iridescent. It doesn't change as the sunlight changes on it.
Thank you, Don. And if I remember correctly, I think it's also called structural color when it's colored due to some structure. And I see there is a question from AC, I believe from California. If the Earth had no atmosphere, would a total eclipse of the moon still look somewhat red?
Oh, thank you, AC. No, if the Earth had no atmosphere, the total eclipse would be essentially black. I don't think very much light would be refracted just by refraction of light on a sharp edge. I think the amount would be so tiny that the moon would disappear when it passed into the Earth's shadow, and you would not see it. Now, how can we test that without getting rid of the Earth's atmosphere? We need to go somewhere else where we're standing on something that has no atmosphere and watch an eclipse. And you know, that could probably be done on the multiple moons orbiting Jupiter or Saturn. It's possible that if we put landers down on those moons and those landers then watch an eclipse of the sun from another moon passing in the sun, or passing into the shadow of a moon. Wait a minute, as I think about that, no, I actually can answer this. Do you know, if you watch Io and Europa, Ganymede and Callisto, the four brightest moons of Jupiter, and I've done this many times, I used to do it with my students, when they pass behind Jupiter, because Jupiter often isn't directly opposite the sun, the shadow of Jupiter is cast to the side, and you can see those moons disappear into the shadow. Or you can see them pop out of the shadow, but you can't see them when they're in the shadow, even though you know from their position they have to be there. They totally disappear because no light gets scattered into the shadow. Yeah, that works. And yeah, we won't see anything, AC. It will disappear completely.
Thank you. And I see a somewhat related question from Marcus Jalakas. So as we know, the sky is blue during the day, and then the sun sets, it gets red at the end. Why don't we see all the colors between red, blue during different stages during the day, depending on?
I mean, why don't we see a whole rainbow? Well, Marcus, when the sky scatters light to your eye, it is scattering the full rainbow. It's not just scattering blue light, it's scattering blue, green, yellow, orange, red. It's scattering all of them. But the law of the scattering, and let's just do a little bit of mathematics here, the law of the scattering depends on the wavelength to the fourth power. And so the scattering goes as 1 over the wavelength raised to the fourth power. That's wavelength times wavelength times wavelength times wavelength. Blue light is half the wavelength of red light. And if you multiply a half times a half times a half, or 2 times 2 times 2 times 2, that's 16. the blue light is scattered 16 times better than the red light. And so it's just that the blue light dominates because it's scattered so well. But all the wavelengths are being scattered. Even at sunset, some red light's being scattered away, but it's predominantly the blue, and then the red comes through. So the answer to your question, all those colors are coming through, but because of the character of the scattering being so dependent on the wavelength, the blue totally dominates.
Thank you, Don. And it's nice that mathematics helps us to appreciate how much the difference is. Now I see a question from Timur, who asks, doesn't the fact that the moon is blue means it consists of another material? I have read about that you can detect the material from the light spectrum it reflects.
Thank you, Timur. The answer to your question is multifold. First of all, when we see a blue moon in the sky, that is because of the light from the moon, which was originally broad spectrum, being scattered coming through the atmosphere. So only the blue gets to our eyes, so it appears to be blue. It's not because the moon is actually blue. But you are right that if you take pictures of the moon with various wavelengths of light, the different rocks scattered different colors differently. And you can find geologic maps of the moon where those colors have been highly accentuated, and you can see the different chemical composition of the rocks on the moon from the different colors accentuated. So yes, you can tell the different rocks from different colors, but the blue light that you see on the rare occasion when it's a blue moon is just because the atmosphere has scattered away the red.
Thank you. Then there is a question from Roger. Why is the sky lighter inside the rainbow?
Inside the rainbow. Yes, below the rainbow it's lighter. Between the two rainbows, I think you probably noticed, Roger, between the first and the second rainbow, it's darker. And in the picture I showed you, the light that's entering the water droplets at a certain angle very nicely is being scattered to your eye. Down below, light is being accentuated, more of it's being scattered towards you, but not particular colors. In between the two rainbows, it's being scattered away. And so that extra bright light that you see in the rainbow, it does look very bright, it's coming from somewhere. And just because of the way it's scattered and it's refracted inside the droplets, more of it's going below the rainbow, some of it's being stolen from between the rainbows, and there are a whole lot more effects. There are some supernumerary bows that have got a lot more interesting effects. I would urge you to go to Les Cowley's website and look at his beautiful diagrams, which will help explain that and show you the angles.
Thank you, Don. There are more questions on rainbow. This one comes from Sue Flower. From a plane, would a sun halo also be 360 degrees? And secondly, why do we sometimes only see some colors of rainbow, for instance, blue, indigo, violet?
All right. First of all, the halos that you see, you don't need to go in a plane to see the whole thing. You can see those when they're right up overhead, and then you do see the whole thing. It's very easy to see the complete 22-degree halo. You don't have to wait till the sun's low in the sky. You can see that when the sun's very high in the sky. In the case of rainbows of different colors, it depends on what the atmosphere is doing, scattering light away. You can get a case, for example, if you get a rainbow at sunset and the conditions in the atmosphere are such that the blue light's being scattered away, you can get a purely red rainbow. I didn't put any pictures in like that, but you can get lovely, almost purely red rainbows where all the blue gets scattered away. Your example you just gave me, where the red has been scattered away and the blue and the green come through, sounds much rarer to me. I've never seen anything like that. And that sounds to me like it would need similar sort of effect to get a blue moon, should be very rare. So if you've got time to type, please tell us, have you seen a rainbow that's just blue and green with no red? Like the red ones with no blue and green are reasonably common, but the other way around, I've never seen.
We'll wait if Sue Flower will type the answer, but in meanwhile, we can go to other questions. And And I see the question from Sean Shields. So the rainbows are circles. Does that mean I will never find the gold at the end?
Yes, it does. But let me tell you something more special about rainbows. Because the rainbow's coming out of water droplets that are just the right position for you to see, when you're standing next to your friend, your loved one, your kids, your parents, and you're looking at the rainbow, you say, look at that beautiful rainbow. You are not seeing the same rainbow as the person next to you. That's your own personal rainbow, and they're seeing a different rainbow. And if you had a condition where the water droplets just cut off so they were in front of you and not in front of them, you could see the rainbow and they wouldn't. That's really your own personal rainbow. And maybe that's better than a pot of gold at the end of it.
Thank you. Another question from Timur. On what does the width of rainbow depend, or it is always the same?
Oh, it is always the same, Timur, for that 42-degree rainbow, and it depends on the speed of light in water, and so the dispersion of the light. When light moves from a vacuum into air, it slows down by a tiny fraction. It's still going close to the 300,000 kilometers per second. But when it goes down into water, it slows down to about 225,000 kilometers per second. It really does slow down. And the blue more than the red, and that dispersion, that amount that it slows down, depends on the material. If you had droplets of liquid in the air forming a rainbow that weren't water and had a different index of refraction, the light traveled at a different speed, then the rainbow would spread out. If you had a liquid up there where the speed of light was less than that in water, the rainbow would spread out more. And a beautiful case of that, in case any of you happen to be wearing them, is a diamond. Light slows down to 124,000 kilometers per second in diamond. All right, that still sounds fast, but it's a lot slower than 300,000. And so the light is dispersed more. And one of the reasons that diamond have got their fire, their incredible flash and beautiful rainbow colors, is because the light slows down so much more. The rainbow is spread out over a much bigger angle. And so there's your answer, Timur. Just go find a diamond. If you haven't got one on you, then look in a jeweler's shop and get a bright light shining on it. Even better, go to the Natural History Museum in London. Up in the mineral collection upstairs at the back, they have got a collection of diamonds where they've got about 260 of different colors, and they've got big ones with bright light shining into them. You can move your head around and you can see this effect spectacularly.
Thank you, Don. And now I see Sue Flower replied, and Don says, thank you for the answer. I have seen one that had yellow, green, and blue a few years ago in Liverpool.
But the red was gone. Okay, Sue, I'm going to do a little research on that after the talk. I'm not going to do that now in the last few minutes we've got left, but you've intrigued me, and I will look to see if I can make some sense of that. Whether I ever get to tell you whether I've made sense or not, maybe we can do that online through the connection in the YouTube. But I'll look it up. I'll see if I can figure that out. That's a new one to me.
Thank you, Don. There is a question from Lucy Brown, who asked, what caused the red sky over China on May 11th?
Oh, I didn't hear, Lucy, about the red sky over China on May the 11th, but red sky, I don't know what was happening in China. You can get some spectacular colors in the sky with either fires or volcanoes. I'm not answering your question, I know, because I don't know what happened in China, but I can tell you that after the big Mount Pinatubo explosion, a volcano in 1991, where I lived at that time in South Africa, the skies turned an incredible, unbelievable color, like egg yolk yellow and purple and just the most weirdest colors. And those strange colors lasted for about 6 months before those aerosols got out of the atmosphere. And so my guess is that something happened in China, probably dust storm given their conditions there, but could be fire. Not volcano, because a volcano I probably would have noticed in the news, but something like fire or dust storm set up conditions in the atmosphere where the red light was what was getting scattered and being seen to produce a red sky.
Thank you, Don. There is Lucy Brown adds that in China, the rivers appeared red the next day.
Oh, that's dust.
Okay.
Yeah, this would have been a monster dust storm in that case, because the dust got into the river and that's what turned them colored. So dust is going to be the answer.
Thank you.
And the scattering of light by the dust would have produced the reddish sky. And of course, the staining of the dust in the river would have produced the red rivers. And China does get some terrible, terrible dust storms when the winds howl down across Mongolia and then across the plains down towards Beijing. They get some big dust storms there.
Okay. There's a question from Jim K. So to determine materials on the moon planet by examining the spectrum of reflected light, it seems that observing those spectra from space rather than ground-based telescopes would be better?
Oh, everything is better from space, Jim. It's always better to get outside the atmosphere. And I think that the geological maps of the moon that have been done with those different colors from the reflectance have been done from orbiting satellites orbiting the moon. Humans, various countries have had many lunar orbiters, and those studies are done not only from space, not from the ground, but from right up close with something orbiting the moon. And then you can test those with ground truth with the rocks that were brought back, both robotically by the Russian missions and by astronauts and the American missions long ago. And now with new missions that are going there, the Chinese are landing on the moon, there are new missions coming. People will be bringing back more rocks, and you can test by actually having the rocks in the laboratory to make sure you're getting it right. I'm pretty confident they are getting it right. The rocks on the moon are not so strange. They're pretty similar to the Earth's crust, and they're pretty well understood.
Thank you, Don. Now a question from Steve Dever. Under the right conditions, can a full moon make a rainbow? And if so, would it be too faint to see with the naked eye?
Yeah, typically what happens, the answer is yes, it could, Steve. That's possible. But the rainbow has got to be the opposite direction from the moon. And I have never seen a rainbow or a bow caused by the moon in the direction opposite the moon. So it probably is too faint. But it's not uncommon at all when it's foggy to look towards the moon and see a bow around the moon, which is called a fog bow, and it will be white. And I didn't put any pictures of that in or explain that, but that's scattering off of water droplets. And they also scatter particular angle. And you get a nice bow around the moon, which is called a fog bow. And you can even get icy fog bows in ice in the sky. And then you can see the whole circle too. You can see the whole thing. And so, yeah, you can see rings around the moon. In fact, that's probably what you've called them when you've seen them in the past. And that's typically scattering off of water droplets. And you won't see any color in that. It'll be white or just pale.
Thank you, Don. Now question from Marisa Muccelli. Does all this also applies to northern lights? Hence, why they are almost always blue-green?
No, it doesn't. The northern lights are completely different. What's happening with the north? Should I do a talk on the northern lights for an Astro-Chat?
Oh, yeah, that would be a good idea. Yes. So.
Okay. All right. In the case of the northern lights, a wind from the sun, a blast from the sun, is captured in the Earth's magnetic field, and it's primarily hydrogen, protons and electrons. And the electrons and protons are bouncing between the north and south magnetic pole here on the Earth. Because they're trapped in the magnetic field. They're moving at incredibly high speed. It's happening right now. It's always happening. And I'll do it in real time. The electrons bouncing from north to south are going north, south, north, south, north, south, north, twice per second. They are moving at a large fraction of the speed of light. Where they come down near the atmosphere, up at the poles, they ram into the molecules of the atmosphere, and they excite the electrons in atoms typically of nitrogen and oxygen. And those atoms glow with particular colors just depending on their electronic structure. And so that green glow is typically, the nitrogen would be the red. I think the green's probably coming from the oxygen. And the different colors there are coming from the atoms being excited by high-speed particles ramming into them. And so the northern lights occur on an oval around the poles. And they come and go depending on how much stuff is being blasted off the sun. And your question actually stimulates me maybe to make the next Astro-Chat about the Sun-Earth connection. And the northern lights would be part of that.
Thank you, Don. And as I look on clock, I see that we arrived just 1 minute past 8. And we have more questions, but time is up. We just keep it to 1 hour. I would like to thank everyone who came to this Astro-Chat, and we had this presentation and Q&A session. I thank Don for this wonderful time in answering and presenting, and I'll ask everyone, please put your feedback at the bottom of this video. Put likes and maybe subscribe to this channel. And hope to see you next time again. Thank you.
Okay,
Bye.
goodbye, everybody.